Thank you, and good evening, Chester. A pleasure to be back here talking about the fourth part of Fiat Lux. Don't worry if you haven't seen or forgotten anything that came before. This is episode 4, which is a self-contained episode of the Fiat Lux trilogy. Yes, a trilogy in 4 parts. I wrote it as a trilogy and then decided to add one in Douglas Adams' tradition. This is Colour in the Cosmos, and I'm going to be talking about colour, and then I'm going to be talking about the cosmos, the colours of stars, the colours of nebulae. So there's going to be a little bit about perception of colour and how we quantify colour before broadening it from simply what colour is all about to thinking about the colours of stars, the colours of nebulae, and then I'll say a little bit at the end about spectroscopy and how we go beyond the colours of visible light. So we can start with what is colour. Is colour a real thing, or is it just a pigment of your imagination? Yeah, and whenever I typed this into PowerPoint, it kept changing pigment into figment. Yes, I had to force it to stay on that. So why do we have colour vision? Well, partly to make rainbows look really spectacular, because without colour vision, rainbows would be really boring. Some people say we have colour vision in order to tell what fruit we ought to be eating, to make sure that we actually only eat fruit which is ripe, from, of course, an evolutionary drive to make sure we're eating the right stuff. Would anybody care to guess which of those 3 fruiting bodies are ripe and which aren't? Without colour vision, very difficult to tell. With colour vision, it is absolutely obvious which ones are ripe and which ones aren't. So some people say that's why we have colour vision. I would argue no, we have colour vision in order to make it easier to read maps of the London Underground. So again, in black and white, almost impossible to tell what's going on. As soon as you put colour back again, right, it all starts to make sense now. So how do we perceive colour? You, of course, know about the human eye. Let's just remind ourselves that light enters the cornea and lens focused onto the retina. And the retina is a collection of photoreceptors, some of which are colour sensitive. So I've just labelled them in this cartoon as if they were red, green, blue, etc. And signals from the photoreceptors ultimately find their way to the brain via the optic nerve. You could say, well, isn't that pretty much the same as what a camera does? Because if we look at the sensor in a digital camera, I'm taking a DSLR, a digital single lens reflex as an example, but it doesn't really matter what type of camera we're talking about. With a digital sensor, we have a whole load of pixels that are sensitive to light, each of which is covered by a filter, if we're talking about a color sensor rather than the monochrome astronomical camera. So we have red, green, blue filters that let through particular parts of the visible spectrum. With a camera that I owned a few years back, I looked up what the actual color response was, and this is what light is let through by each of the red and green and blue filters on this digital camera. Very roughly speaking, you can say that the visible spectrum is split into 3, and the red and the green and the blue clearly overlap in terms of their response to make sure that no wavelengths are missed. And you might say, well, if that's how cameras work, then the human eye must sort of be pretty much the same. Red, green, blue sensitivity that covers the whole of the visible spectrum. Well, yes and no, because when you look at the response of the human eye, it is actually very different. The blue response there is relatively narrow and covers only a small range of the visible spectrum, but look at the red and the green. The red, in fact, covers the entire visible spectrum. If we assume that human vision is nominally 400 nanometers to 700 nanometer wavelengths, the red sensitivity covers the whole of the spectrum. Notice also, where does it peak? Well, the red doesn't peak in the red. The red actually peaks in the sort of yellowish, greenish, because it's right next door to the green. This is why biologists don't refer to these photoreceptors as the red, green, blue photoreceptors. They refer to them as the long wavelength, mid wavelength, short wavelength, because describing them as red, green, and blue is a little bit misleading. Well, yes, it is misleading, but I'm so used to referring to 3 colors as RGB for red, green, and blue, I'm going to continue to do that, even though the biologists refer to them as L, M, and S. And just as a reminder, because we're dealing with astrophysicists here, correction, astronomers here, the rods, the non-color sensitive part of the human eye, the rods have a sensitivity that looks a little bit like that, which is why astronomers use red lights, because if you want your color vision back again, you can switch on a red light to read your star atlas or to find out where your feet are or whatever, and switching on red light doesn't influence what the rods are doing because the rods are not sensitive to red. So you can use red light essentially virtually as bright as you like, and it will not destroy your night vision because the rods don't care about red light. Okay, we have 3 sets of color receptors, which I'll still continue to call R, G, and B, so-called trichromatic vision. But not all animals have 3 colors in their photoreceptors. Some have less, some have more. So for instance, there's an animal that has a dozen photoreceptors, and notice from the spectrum at the top there, it goes from the extreme red, arguably pushing into the infrared, throughout the entire visible spectrum, and a few photoreceptors that seem to be dedicated to UV. Anybody care to guess what that animal is? Heard of different things. What was that? Bat? And? Owl. Interesting. Bat and owl. Hey, somebody said it. Yep, mantis shrimp. Mantis shrimp, I don't know why, but mantis shrimps have incredible vision. I assume it's related to what they eat, but why they need a dozen photoreceptors, why they can't get away with an infrared, an ultraviolet, and something in between, I have no idea. There is presumably some evolutionary drive to do that, but I really don't know what it is. So you could ask, well, okay, some animals have got less, some more, so why do we end up with 3 in our color vision? Well, it's not surprisingly because of evolution. If you look back 100 million years or so, well, we were small furry rodents. When dinosaurs ruled the earth, we were small fluffy animals like this. We were nocturnal. Coming out in the day was a bad idea because you get stomped on or eaten by dinosaurs. Once the dinosaurs were removed from the surface of the earth, that allowed us to come out during the day and survive. And so we went from nocturnal to diurnal. And so now it was beneficial because we're now working in sunshine to actually have color vision. And so over 100 million years or so, genetic mutation basically brought back our color vision. I'm not claiming that humankind is necessarily the peak of evolution. I mean, who knows where evolution will take us next? I mean, there's no real telling. Of course, visible light, only part of the full electromagnetic spectrum. It just so happens, well, no, it doesn't just so happen. Visible light gets to the Earth's surface, which is why, of course, we've evolved to be sensitive to the visible part of the spectrum. There happens to be a window, in other words, a relatively transparent part of the atmosphere in terms of the wavelength. Virtually all light that enters the atmosphere makes it to ground level. Only a few percent is actually absorbed. 90-something% makes it to ground level, clouds notwithstanding. And of course, there's a radio window as well. We can't really get much UV, and only a little bit of infrared comes through to the ground. So although it's fine for us to look with our eyes at the night sky, if we want to actually observe the universe in the infrared or ultraviolet, then ideally we want to put spacecraft above the Earth's atmosphere. That doesn't stop us putting visible light telescopes above the Earth's atmosphere, such as the Hubble, for instance, but that's not because the light gets absorbed by the atmosphere. It's simply because the atmosphere is turbulent, and so it would blur our detail of more distant objects. The little cartoon I showed earlier, showing that there are photoreceptors on the back of the eye there, okay, cones and rods. Cones give us the color vision, the red, green, blue. Rods for night vision. Let's forget the rods and just concentrate on the RGB cones. That cartoon is way too simple because human eyes are much more complex. If we look at what's actually going on the back of the eye, yes, we have a whole load of photoreceptors, but we have a completely different layer of receptors, or at least cells, which are neurons. We have neuron cells in the eye. If you think that neurons are just part of the cells in the brain, no, there are a whole load of neurons in the back of the eye. And that means that we do, in fact, have some image processing capability. Not in our brains, we have image processing capabilities in our eyes, literally in our eyes. If you think of what's going on in a camera, you can say, well, light hits the various pixels in a camera, and we get all of the information from the red and the green and the blue pixels. What happens to that information in terms of how much light has arrived that is red, how much light has arrived that's green and blue, etc.? Then the camera takes that information and virtually maps it directly into the final image. Not strictly true, because the amount of red, green and blue can be adjusted in order to make sure the color balance is essentially correct. But roughly speaking, the red that hits the chip is the red that we see in the final image that we get out of the camera, which may or may not be stored on an SD card. Eyes are very different, because although in principle we have red, green, blue photoreceptors, what happens to the information that comes from those red, green, blue photoreceptors is very different from what happens in the camera. It goes through these neuron cells. It goes through a neural network before getting sent to the brain. In other words, the red, green, blue signals that are coming in on the back of the eye are mixed together in some weird way by the neurons before that signal is then sent on to the brain. This neural network here, it could be, for instance, adding together the response of red and green. It could be looking at the difference between green and blue. Or it could be looking at how much is coming in on this photoreceptor versus how much is coming in on a photoreceptor neighboring this one. So an awful lot of processing is done by the interconnection of these neural cells in the back of the eye. I can show you that a lot is being done, far more than we often appreciate, by giving you a little bit of a taste of how this actually works in practice. Before I do this, can I just ask, is anybody here colorblind? One person. I'm sorry, sir, this is not going to work for you, I don't think. We can see that what comes in is not the same as what goes out by looking at this very simple example. There's a couple of Rubik's cubes here, 5x5 tiles. I'm only interested in what's going on the top face of these cubes. If you look at this cube on the left and look at this top face of 5x5 tiles, how many of them are blue? The number keeps changing. Make your mind up. How many? 4. Most people think 4. Look at the cube on the right-hand side. Again, 5x5. How many of them are yellow? 7. Okay, so the consensus appears to be 4 blue on the left and 7 yellow on the right. Yeah? Okay, are you prepared to put money on that? You can tell from the tone of my voice that 4 and 7, in terms of how many blue and how many yellow, is not actually the correct number. If we look at the tiles, the 4 blue tiles that you've identified on the left and the 7 tiles on the right that you've identified of yellow, they are actually the same color. All 11 of them are the same color. You only think they are blue and yellow because that is what the neurons in the back of your eye are telling your brain. If I were to remove all the pixels other than those 4 and those 7, if I take all of the other pixels away, what you were actually looking at were 4 grey tiles on the left and 7 grey tiles on the right. You only thought they were blue and yellow just because of the other neighboring pixels in your field of vision. In other words, the neural net in the back of your eye was basically saying, these appear to be a lot bluer than most of the other pixels I can see. These on the right appear to be a little more yellow than all of the other pixels I can see. And your brain then tells you, those are blue, those are yellow. But that wasn't what the red, green, blue receptors were actually firing in the back of your retina. It's only what your brain interpreted after the back of your eyes did this neural processing. And although it's not strictly speaking color, I can give you another example that this processing is always going on in the back of your eye by giving you another example and asking you about the square on which A sits and the square on which B sits. And I can ask you which of those is the brighter or the darker shade of gray, and you will come to a conclusion as to which you think is darker. If I then map out by just bringing in a couple of masks, I think you can now see that A is exactly the same shade as B. Okay, now that you know that A and B are exactly, not similar, they are exactly the same shade of grey, I've checked it. Now let me take those two masks away. So now you know that A and B are the same shade of grey. What's your eyes and your brain telling you? Your eye is doing some image processing, telling the brain what it thinks you need to know, which is not actually how much light is arriving. Just like before, it's not actually telling you what is the color of these pixels in the image. So you can easily be fooled because your eyes and your brain are doing an awful lot of processing when you don't even know it's doing the processing. You can't just assume that what you see is what's actually there. Hence, what we see is not the same as what a camera picks up. So how can we actually quantify color? Well, if you ask a physicist, how do you quantify color? The knee-jerk response is usually, well, we have a spectrum. Not that spectrum. For those of a certain age, you'll recognize that, but no, we're talking about this spectrum, the one that Isaac Newton set up in order to try and reproduce the front cover of Pink Floyd's Dark Side of the Moon. So he did this in the 1660s, and of course we now know that white light is actually comprised a whole set of colors, which you can see if you send the light through a particular optical apparatus. It could be a diffraction grating, could be a prism, or it could just be a chunk of glass, which is technically neither. When light passes through glass, doesn't really matter whether it's an odd bit of glass or a triangular bit of glass or a part of a microscope or part of a telescope, it'll generally reveal its wave nature. And as far as color is concerned, it's not the amplitude of the electric and magnetic wave that's part of the electromagnetic spectrum. It's not the amplitudes that matter, it is purely this wavelength, the distance between adjacent crests. And for most humans, our normal vision, it's normally accepted that most people can see roughly wavelengths from 400 nanometers to 700 nanometers, 0.4 microns to 0.7 microns. There's a little bit of variability. Some people can see a little further into the infrared, some can see a little further into the ultraviolet. But that's not all there is to color, because color is not a one-dimensional thing. For instance, where is beige in the spectrum of all colors? Where's brown? Red, orange, yellow, green, blue, indigo, violet, etc. A single line gives us the spectral colors, the colors that by definition are part of the spectrum, but that is not all colors. If we want to show all colors, then a single line is not good enough. And there are a number of ways in principle we could quantify color, but one that has become standard is a two-dimensional color space. It goes under the name of CIE. That's what CIE actually stands for. We're not going to worry about how this standard came about, but many decades ago, people said we need a way of standardizing what we mean by color, and this has now become effectively an industry standard for how we define colors. We are not going to worry in this talk about what the axes actually are. We'll just treat this as a two-dimensional color space where every color has a particular position in this two-dimensional space, and we're not going to worry about the definition of how we come about its actual coordinate in terms of x and y. If you're interested, you can go and Google CIE color space and you can find all about it. I'm sure there's a few hundred web pages dedicated to this particular definition of color space. We're just going to assume that we're going to use this particular definition. Spectral colors actually occupy the outer part of this particular weird-looking space, from extreme red at this end to extreme violet at this end. One thing we have to bear in mind is that digital devices of any kind are limited as to how many colors they can display. Even here, I can tell you that what I see on my laptop is not the same as what you're seeing on the screen, simply because the people that made this particular display are not the same as the people who made that particular display. And therefore, the colors and exactly how red, how green, how blue does it look are not going to be identical. Hopefully, they are similar, but they're not identical. Every digital device, regardless of what it is, can only display a limited range of colors called a gamut. And it's not going to be every color that's inside that particular shape. The particular device we're talking about, in this case what you're looking at, the projector, can only display inside a triangle defined by the primary red, green, blue that are part of the display system. So in other words, if we have a particular projector which defines that as red, green, and blue, any color inside that triangle can be made by mixing a certain amount of red, certain amount of green, certain amount of blue. But only colors inside that triangle can be generated. That red, green, blue triad there cannot generate any colors outside the triangle. That is why, for instance, all of these colors that are further top left of green, they pretty much all look the same, because the projector is incapable of actually showing you the true colors of what should be in there, because it only has a particular gamut, a particular range of colors that it can display. And remember, that is not necessarily the same for every device. Of course, the manufacturers of every display, every projector, etc., try and make that red as close to that corner as possible, that blue as close to that corner, and green as far up here as possible. The bigger this triangle, the greater the richness of colors you can display. If that triangle is small, there's a very limited gamut that you can display. So manufacturers will try and make that triangle very big, but there is a limit to how you can manufacture either an LED or an LCD screen that's capable of showing you a range of colors. So that is human perception, how we see colors and how colors are actually generated. Before we come to the break, I'm going to say a little bit about colors of stars, and then we'll take a short break for a cup of tea, and then I'll return to talk about other aspects of colors in the cosmos. So let's deal with colors of stars. You may say, when we look out into the universe, we see stars of all sorts of colors. There are hundreds of billions of stars in the Milky Way. Presumably, they're all different, and presumably, regardless of where we throw a dart at this and find out where it lands, presumably there's a star of that color. No. Stars have very specific colors when plotted in this color space. You may be surprised to learn that the stars are very much limited to that particular locus there, that particular range of colors. We can't have stars that are right at the top of this diagram. We can't have stars at the bottom left-hand corner. We can have stars in the bottom right-hand corner. Those are the cool stars, the red giants, etc. And as stars get hotter and hotter, the color tends to move towards white, which is the middle of this particular color space, and ultimately will go through white and out the other side into a rather more bluey color, a sort of blue-white, as it's often described. White with a hint of blue, or bluish white. But those are the only colors that stars can be. They cannot be arbitrary because that is dictated by the laws of physics. We are not going to go into the detail of how quantum theory defines that you can only have certain colors radiated by stars. Again, this is something you can go and look up if you're interested. But we know, for instance, that if we take a chunk of material, doesn't matter that this is a chunk of iron, not a star. Doesn't really matter what it's made of. What matters is, as a function of temperature, we see different colors. When things are quite hot, we see relatively white colors. As things cool down, they go more yellowy, orangey. When things are only relatively warm, or at least a few hundred Kelvin above room temperature, then they're red. And when they're cooler still, well, they will be emitting infrared, but we don't actually see them glow as such. This range of colors is pretty much the same, regardless of whether we're talking about chunks of iron or whether we're talking about stars. So let's have a look at why that is. This is a rather neat little animation that's put together to tell us what sort of range of colors will be emitted by an object of a given temperature. The temperature is up there in the top right. It's called blackbody because that's part of how physics is defined. The fact that stars are glowing brightly, don't let that put you off. Blackbody just means an object that is producing light simply because it is hot and by no other mechanism. So there's a temperature, and this is telling you what intensity of light you get as a function of wavelength. Ultraviolet on the left, longer wavelengths on the right, that's infrared. very short wavelengths at this end, 1 micron, 2 micron, 3 micron, and there is where the visible spectrum is, between 0.4 and 0.7 microns. So when an object is relatively cool, I mean 1200 Kelvin is pretty damn hot for most of us, but as far as a star is concerned, it's fairly cool. Most of the radiation is there in the infrared part of the spectrum. And the arrow indicates that's where the maximum is. It's quite definitely in the infrared here between 2 and 3 microns wavelength. If I now bung the temperature up a little bit to 1500 Kelvin, two things happen. More light is given off by this object, which is why the curve is now higher, and the peak, indicated by the white arrow, is shifting away from the infrared towards the visible. It's still in the infrared at this point, but it's shifting towards the visible. I'm going to rescale this, otherwise when I go to higher temperatures, this is going to go simply off the chart. So I'm going to rescale this to make sure this peak doesn't get too high. But the important thing is to watch where the peak actually sits. If I go to 2000 Kelvin, then the peak is still quite definitely in the infrared, but notice that some light is now being radiated in the red and the blue part of the visible spectrum. So at this temperature, if you looked at an object that had this particular temperature, you would see it glowing quite brightly in the red part of the spectrum. You would hardly notice that there's any blue in there at all. If we push to 3000 Kelvin, we're now at the sort of temperature of a typical red giant, for instance. So think of this as Betelgeuse, if you wish. We're now at 3000 Kelvin. The peak is quite definitely still just in the infrared. It's just off the red end of the spectrum. But notice there's a lot of red light being generated by a red giant and a little bit of blue light. So not surprisingly, a red giant looks red. No surprise there. So it's actually emitting across the entire visible spectrum, but there's something like 10 times as much light coming at the red end as the blue end, and hence the object will appear red. If we bung this temperature up still further, now we're at roughly the surface temperature of the sun. So what we have now, the peak of the radiation is now coming in the visible part of the spectrum. But notice that the amount of light in the red and the amount of light in the blue part of the spectrum is roughly similar. Yes, there's a slight difference, but to a first approximation, the sun is emitting at all wavelengths, and technically it's emitting a little bit more in the green and yellow than it is in the blue and the red, but it's emitting right across the visible spectrum. And so this star looks essentially white, or at least white-ish. If we push the temperature up further, then this peak gets pushed even further over and is now peaking in the ultraviolet. And now it's peaking in the ultraviolet. We clearly have far more blue light than we do red light. And that's why these stars, A stars or B stars or O stars, are described as bluish white, because although they are emitting light across the entire spectrum, they are emitting rather more at the blue end than they are in the red end. So that's why they are called whitish stars. So to recap, if we change the temperature, let's start again with red giants. If the star is relatively cool, then it's mainly red and a little bit of blue. When we get to the peak being in the visible spectrum, essentially all wavelengths are covered, so it's essentially white. And if we go to even higher temperatures, then it peaks in the ultraviolet and there's a hint of blue in the spectrum. At no point does the star actually look green. Stars are either red or whitish or bluish whitish, but there's no such thing as an emerald green star, because that would disobey the laws of blackbody radiation as discovered a century or so ago and dictated by the theory of quantum mechanics. So again, we're not going to go into details, but basically stars can only have one of these types of shapes, which depends on the temperature and essentially nothing else. So that's why there's only a limited locus in that color space that I showed you, because they have to have this particular shape, and the position of where the maximum is will shift according to the temperature. But because the shape is dictated by quantum theory, you can only have certain stars of certain colors. If we were to plot out luminosity of the star as a function of its surface temperature, we get the familiar HR, or Hertzsprung-Russell diagram. And remember, these colours here are essentially the same as the colours we get if we heat up a chunk of metal. There's really not that much difference. Again, whitish if it's hot enough and reddish if it's cooler. The sun is in the middle there. It has a luminosity of 1 simply because we've decided to define luminosity in terms of the luminosity of the sun. So by definition, that's 1. And the surface temperature of the sun is about 6,000 Kelvin or so. We know that when we look out into essentially the Milky Way rather than other galaxies, we get a pretty good idea of how stellar evolution works. And we know that stars populate the Hertzsprung-Russell diagram not uniformly over the entire square that I'm showing here, but we know that there are particular traits of stars that follow particular parts of the Hertzsprung-Russell diagram. For instance, we know that the large stars tend to be in the top right-hand corner, and the smaller stars, such as white dwarfs, for instance, tend to be somewhere in the lower left-hand corner. This is a result of simply examining millions, if not billions, of stars and getting an idea of their relative sizes and where they fit in terms of luminosity and their surface temperature. Similarly, we can map out the stars and we find that the really massive stars tend to be in the top left-hand corner and the rather low-mass stars appear to be in the bottom right-hand corner. So the Hertzsprung-Russell diagram actually contains some useful information about the properties of stars, either their size or their mass. And although it's not obvious at first sight, we can use this to actually verify, for instance, if we have a star cluster, we can perhaps see already that there are different colored stars in there. No green stars, but there are different stars. There's probably a few red stars, a few blue stars. If we have a look at an image like that, we can actually use the colors of stars to actually tell what the age of the cluster is. And I'll tell you how we do that after the break. Thank you. Okay, we're back from the tea break, and I was telling you about the Hertzsprung-Russell diagram in which we plot stars with their luminosity on the vertical scale and color on the horizontal scale. And by looking at the properties of stars, we find that large and small are in those corners, and large mass and small mass are in those corners. And I finished the first half of this talk by saying that we can use that information to actually identify the age of a star cluster, simply by taking an image like this, which captures the brightness of the star, effectively the luminosity, and the color of the star, and then plotting all of these brightnesses and colors against each other. And we find that apart from the fact we do get some giants and some dwarfs, we'll find a lot of the stars lie along the main sequence, the diagonal that we're showing there. So at the moment, we're going to ignore the fact that some stars will be off this diagonal in the top right or bottom left. We're just interested in those stars that follow the main sequence. If you remember, the really massive stars are in the top left, the blue supergiants. If they're really massive, gravity is very strong. They have to burn their fuel very rapidly to maintain pressure against gravity, which means they have very short lives. Whereas in the opposite corner, in the bottom right, red dwarfs are relatively low mass, and even though they don't have much fuel, the fuel lasts an awful long time, and so they have very long lives, perhaps trillions of years, compared to millions of years in the top left. So if we were to plot out, for any given star cluster, if we were to plot out all of the main sequence stars, we can get an idea of their age, because we know that in the top left, they don't last very long. So if we find the main sequence goes as far as the white arrow there, we can deduce that this cluster must be quite young, because if those blue supergiants don't last long, but they're still there, then this must be a young cluster. And as the age of the cluster continues, basically, we get less and less of the main sequence. So if the main sequence only goes as far as that point, when we plot out all of the stars we can see in the cluster, then, for instance, the cluster is only something like 100 million years old. We deduce that from knowing the age of stars at particular points in the HR diagram. And if we find the main sequence that we get by plotting out the stars in this cluster only takes us as far as the sun, that's the sun point there, we know that the lifetime of our sun is roughly 10 billion years or so. The sun is middle-aged, halfway through its life. So if the main sequence only goes to that point, then we deduce the cluster must be about 10 billion years old, because all stars that are more massive than our sun have already died, and hence we don't get any dots beyond that point. So we can deduce the age just literally by seeing where that main sequence stops when we plot out all the stars that we could see in a cluster. So it's a very neat way of using the colors of stars to tell us about the age of a cluster. So we can deduce age simply by taking an image and getting intensities or luminosities and colors of stars. When we think about all the colors that are out there, I've said that most stars are reddish or whitish, maybe blue-white. What do we find if we add up all the light of all the stars? In other words, what do we find for taking all the stars in all the galaxies? Well, we can't do this for all the galaxies, but if we take a reasonable subset of galaxies and add up all the light of all the stars, what do we find is the average color of the universe? Well, some astrophysicists that have got way too much time on their hands have basically taken 200,000 galaxies within about 2 billion light years and effectively, digitally, added up all the light from these stars to find out what would the average color of the universe look like. They deduced that the average color of the universe is that. Perhaps you can see it's just slightly different from the white background of this particular PowerPoint slide. It's sort of beige, which is about as boring as the universe can possibly be. But they decided that beige wasn't a good way of publicizing it, so they decided to find a better name, and they came up with either cosmic latte or my favorite, skyvery. So that's quite a nice one. But it is a bit boring to realize that we live in a beige universe, but okay. So we've been looking at the perception of color, how we quantify color, and the colors of stars. We're now going to have a look at the color of nebulae and see how that is different. If we think about stars, and as far as this is concerned, I'm treating a galaxy as simply a collection of stars. Yes, galaxies are more than that. They have a whole load of gas and a whole load of dust and a whole load of other things. But let's just assume that a galaxy is effectively just a collection of 100 or many hundreds of billions of stars. When we look at all of those, we find that there's a continuous spectrum. Each star will emit light across the spectrum. Yes, some stars are red, which means they emit more red than blue. Some stars are bluish, which means they emit more blue than red. Some stars, like our sun, emit across the whole of the spectrum. So I'm not suggesting that is what every star looks like, but the point is that every color is represented on the spectral sequence there. That's rather different than if we look at a nebula, where if we look at, doesn't really make a lot of difference what the nebula is, but most nebulae are made mainly of hydrogen and a few heavier elements as well, but generally speaking, a lot of hydrogen. And we find that the spectrum is not every color that can exist in the spectrum. We find quite definitely some spectral lines, and other parts of the spectrum are apparently completely black, completely absent of any emission of light. So why is it that stars appear to emit at all wavelengths, whereas nebulae only emit at certain specific wavelengths? Well, the origin is in the nature of the atom. So remind you that an atom is a positively charged nucleus and negatively charged electrons. That is not a very good map. That is not a very good diagram or representation of an atom, because it makes it look like all the electrons are the same, whereas in fact all the electrons are at different distances from the nucleus. That is not a particularly great diagram either, but at least it represents the fact that different electrons are at different distances from the nucleus and hence will have different energies, and it's the energy that's actually critical. Unlike a solar system, an atom is not flat, but for representing an atom on a two-dimensional piece of paper, we often still think of it that way. We should really think of an atom as being concentric shells, but it's just easier to draw them as rings, as if they were orbits around a solar system object like the sun. But the important thing is that different electrons have different energies. And if we think about an electron that can exist in two different energy levels, so I'm representing that as two different radii, in other words, two different distances from the central nucleus, which I haven't shown, then if an electron drops down from a high energy to a low energy, then on losing that much energy, the energy is radiated away as a photon of light. And the amount of energy that's taken away is precisely the difference of those two energy levels. Similarly, if an electron exists in a low energy level and a photon comes in, where that photon has just the right amount of energy to push the electron from the low energy to the higher energy, then an incoming photon can make the electron jump. The important thing is that for any given atom, the electrons have particular energies which are dependent on the atom. In other words, quantum theory tells us if you've got this atom, doesn't matter which one we're talking about, let's just say we're talking about a hydrogen atom for the sake of argument. If we're talking about the hydrogen atom, then the electron can have only specific energy values. It can't have any energy value it likes. That is what quantum theory is all about. The energy levels are quantized into particular values which depend upon the atom. And the amount of light, the wavelength of light or the energy of light that is emitted or absorbed, depending on which way the electron is jumping, from low to high or high to low, the energy of the photon emitted or absorbed is the same as the difference of two energy levels in the atom. And if the energy levels of the atom depend on which atom they are, then the energy of the photons that were emitted or absorbed will depend on which atom we're talking about. Quantum mechanics tells us what the relationship is. Low energy to high energy, the red end of the spectrum is the lower photon energy, the blue end is the higher photon energy, and that corresponds to the short wavelengths at the blue end and the long wavelengths at the red end. So there's a relationship between energy and wavelength, and we already know there's a relationship between wavelength and color. So that means if an atom has a particular set of energy levels, then there's a particular set of colors of light that can be emitted or absorbed by that particular atom. So this is still a rather cartoony way of representing, in this case, not hydrogen, but an atom with a large number of electrons. But the energy of the electrons in an atom are characteristic of the atom. The energy levels in hydrogen are not the same as the energy levels in helium, which are not the same as the energy levels in carbon, or nitrogen, or oxygen, or any other element in the periodic table. Hence, a particular atom will absorb or emit photons with a characteristic pattern, a sort of fingerprint, if you like, that tells you which particular atom you're dealing with. So if you see characteristic lines of color, you can look up which atom must have produced these colors. It can't be an arbitrary one. It must be either hydrogen or helium or lithium or beryllium or all the way down the periodic table. When we look at, for instance, the light that can be emitted by hydrogen, there's a very strong line at the red end of the visible spectrum. There's actually one at the blue end as well, called hydrogen beta. We're not going to worry about alphas and betas. They're just different colors of light that this particular atom can emit. Oxygen emits at this particular wavelength. It isn't only those wavelengths. Atoms can emit infrared and ultraviolet. These are the ones that just happen to sit in the visible part of the spectrum for the two most common elements in a nebula, hydrogen and oxygen. So we can ask ourselves, why the difference? I've just said that light from a nebula is made up of a discrete set of colors that depends on what the nebula is made of. Probably hydrogen, maybe mixed in with a few other things as well. Quite often, when you look at nebulae, you find that they are a mix of hydrogen, oxygen, sometimes sulfur as well, for instance. And if the light from a nebula is made of a few discrete lines, depending on the atoms, and we've already said that for stars, we know that they emit across the whole of the visible spectrum with a different balance between how much red and how much blue, depending on how hot the star is, well, that's fine, but they're made of the same stuff. Nebulae and stars are both made of hydrogen and heavier elements. So if they're all made of the same stuff, why do nebula give us one type of spectrum and stars give us a different type of spectrum? The difference is all down to the density of how many atoms are in the material that's emitting this light, or possibly absorbing the light. Let's just stick to emission of light from a particular set of atoms. If the atoms are well separated and don't know about each other, And that means atoms that are separated by much more than the diameter of an atom, let's say for the sake of argument, at least many, many, many nanometers, possibly even microns. If they're that separated, they really don't know about each other's existence, and each of them will emit light according to the rules of quantum theory. They'll emit light of particular colors depending on the atom we're dealing with. But if the atoms are so close together they're continually interacting with each other, although light is emitted by the acceleration of electric charges, if the atoms are really close to each other, then all of the light emitted by all of these atoms get effectively smeared out into a continuous spectrum. So the difference between are we expecting to get only a few colors or are we expecting to get all colors in the spectrum of light and colors emitted from a given object, it's all about the density of how close the atoms are to each other. So we can ask the question, how many atoms are there in 1 cubic centimeter, one sugar lump if you like, of material? If we start with very dense materials, a lump of metal has that many atoms per cubic centimeter. A huge number, I can't even remember how many millions that is, 100,000 million by the look of it. Huge numbers. That's why when you heat a lump of metal up, it glows just like stars because effectively they're very dense. What about Earth's atmosphere? We may think of the Earth's atmosphere as being almost nothing because we can move through the Earth's atmosphere at ease, but it still contains a huge number of atoms or molecules per cubic centimeter. If we go to the surface of the sun, the photosphere, perhaps it's surprising to realize that the surface of the sun is more rarefied than the air in this room. But if we look at how many atoms per cubic centimeter, we can see it's still a huge number, but it's actually small compared to the density of the Earth's atmosphere. If we go to the sun's corona, now we are genuinely getting to relatively small numbers. Here we've only got 10 million atoms in 1 cubic centimeter of the solar corona. That changes as a function of distance from the sun. Let's just sort of take an average. If we now say, what about an interstellar nebula? What if we were to look at the Orion Nebula or the Horsehead Nebula or something like that? How many atoms in 1 cubic centimeter? Now we're talking about only thousands rather than millions. And if we go to the interstellar medium where there's effectively no nebula present, then the number might be as low as maybe 1. 1 atom per cubic centimeter. That is not the rarest gas we know about because the intergalactic medium is even lower. Strictly speaking, not 0, I just mean there's very unlikely to find an atom in any given cubic centimeter. You might find 1 atom in a cubic meter, for instance. That's the sort of density of the intergalactic medium. That doesn't sound like much, but there's a huge distance between galaxies. So actually there's an awful lot of gas between galaxies. It's simply very rarefied because the distances are so large. But when we have that sort of density of atoms, remember it's the interaction because of the proximity of atoms that leads to a continuous spectrum. So a lump of metal will have a continuous spectrum, so will the Earth's atmosphere, so will the photosphere of the sun. We know that when we look at the sun, we effectively get a continuous spectrum. That's why our eyes have developed the way they have. But when we go to the solar corona or nebulae or anything more rarefied than that, these atoms are so far apart, they are effectively not interacting with each other, and so each atom will give the characteristic colors that are dependent on the individual atom that they are made of. Quantum theory will say we'll get a certain set of colors from hydrogen, a different set of colors from helium, a different set of colors from oxygen, etc. So simply by looking at what colors are there, we can tell what the various nebulae are made of. So anything beyond that point will be discrete colors. I've just shown what hydrogen looks like, but it will depend on what the principal element that we're looking at is. So that's why we have a difference between the colors of stars and the colors of nebulae, simply because are the atoms interacting, yes or no? Okay, there's a little bit of a gray area in between, but most of the objects we're interested in can be separated out into dense and rarefied, giving us continuous spectra or giving us discrete line spectra. Let me finish with just a few comments about spectroscopy and what you might call false color. So I'm not going to talk about the fact that we can use spectrum of a distant star, and we can use Doppler shift to tell if the star is moving away or towards us. We can use that for finding exoplanets, for instance, by looking at the light from a star and seeing if the spectral lines shift as the star moves backwards and forwards because of a circulating planet that makes the star wobble. Well, I am going to mention the fact that the light from a distant object can be used in the context of a redshift, especially in the context of a cosmological redshift. Because the universe is expanding, objects are moving away from us, and when we look at the light gets shifted towards the red end of the spectrum. The light gets stretched out, if you like, because the light is traveling through a universe which is continually stretching, if you want to think of it that way. As the light travels through space, the light gets stretched out and the wavelength increases. The amount that the light is shifted is called the redshift, and its value, usually denoted by the symbol Z, is how much has it shifted compared to its original wavelength. In other words, if its original wavelength was that much and it ends up being twice that much, it's being shifted by an amount equal to the original wavelength. If the wavelength doubles, then we define the Z as 1. A distance at which the redshift is equal to 1, in other words, the wavelength doubles because of the expansion of the universe. The distance at which the redshift would be 1 is approximately 10 billion light years. So, looking at the colors of distant objects, strictly speaking, the spectra of distant objects, we can get a really good handle on the distance, because if we understand how the universe is expanding, there's a little bit of controversy as to exactly what the expansion rate is, because different techniques give us slightly different values that differ by a few percent or so. But roughly speaking, we know how fast the universe is expanding, and so we can determine that doubling the wavelength of a distant object corresponds to a distance of approximately 10 billion light years. A couple of years ago, I gave you a talk which I called Ancient Light, in which I imaged a very distant quasar. There it is, the most unspectacular image you'll ever see. This is a quasar at a redshift of 4.3. So its wavelength when it arrived on Earth is 5 times bigger than the wavelength when it left. I didn't measure the redshift. I looked it up for this particular object, and I decided to see if I could photograph this object with my Nikon camera, not with a telescope, just with a Nikon camera and a lens. When I originally showed it, I said, there it is, there's a monochrome image of that little spot there. But given that this talk was about color, I thought I would actually go back and image it with color, and it's even less spectacular, because when you're looking at images with red, green, and blue, it's very difficult to see what's going on. I separated out the red, green, and blue, and the red is just about visible. You can just about see that, I think. You might not be able to see the green, but I guarantee you it is actually there. And I could find no sign whatsoever of anything in the blue channel of this RGB image of this distant object. It's at a distance of some 25 billion light years, some huge distance. It's receding from us. Remember, a Z of 1 corresponds to 10 billion light years. This is 25 billion light years. This is receding from us at about twice the speed of light. I'm showing you these 3 images where you can see it in the red and basically you can't see it in the blue, because this is a way of measuring redshift. It's not a good way of measuring redshift in the sense we really want to take the spectrum and see what the spectrum looks like. But simply by taking images of an object at different wavelengths, you can get a sort of a proxy, if you like, for the redshift. And I'm telling you this because that's precisely what the James Webb Space Telescope has done. If time allows, it looks at distant objects and takes a spectrum and measures that spectrum to determine the distance. But sometimes it hasn't got time to do that, especially when it's got lots of objects in its field of view to look at. And so what it has done for some objects is to say, well, does it appear at long wavelengths and does it disappear at shorter wavelengths? And we've got that for a few different objects here. It's quite definitely there at long wavelengths, but it seems to fade away at shorter wavelengths. Just like I showed you that I could see the quasar in the red, I couldn't see it in the blue. This is infrared, so it's not simply red, green, blue, but the colors above there simply remind you this is the long wavelength end and this is the short wavelength end of the data that James Webb is taking. This is called photometric redshift. It gives you an idea of what the redshift of the object is without having to take a spectrum, which generally speaking takes longer because you're spreading the light out over a huge number of wavelengths and you have to expose for much longer to get a decent spectrum from which you can measure a redshift. So this is the way James Webb and other telescopes determine roughly what the redshift is, and if you take enough individual images at different wavelengths, you can get a pretty reliable indication of what the redshift is. It's always good to go back and actually take a spectrum to verify what the redshift is, but this has been done for quite a few objects. Occasionally, the object is a bit redder or a bit less red than you would expect, and sometimes the distance you get from this photometric redshift is not actually accurate, which is why some of the early data from James Webb said this galaxy appears to be this distance, but later they said, oh, sorry, no, it isn't. We've gone back, we've actually taken the spectrum, we've determined the actual redshift, and it turns out that this galaxy is a bit redder than we thought, which means it's not at this distance, it's actually at that distance. So some of the early estimates from James Webb were revised because the original photometric redshift was replaced with a more accurate spectroscopy redshift. We can go beyond color because what we've been talking about is essentially red, green, blue and visible parts of the spectrum, but I've just shown you a James Webb image. And you can ask the question, which is something that continually crops up, are any of the, not James Webb, but are any of the Hubble Space Telescope images actually an indication of the colors that you would see if you were standing in front of this object? The classic being the Pillars of Creation that was imaged soon after it went up in the 1990s and then re-imaged every few years as it got better and better cameras. So if we look at the actual color image and think about the red, green, blue images that actually produce that, the elements that were imaged, not by having a red filter, a green filter, and a blue filter, which is the way we normally take color images, with a telescope like the Hubble, if you want to extract meaning from the images rather than a nice pretty color image, you don't necessarily put in red and green and blue filters. You put in a filter that specifically shows you what the hydrogen light is doing. In other words, you choose a filter that lets through the particular emission line produced by hydrogen atoms. And then you put in a filter that lets through the particular light that is produced by sulfur. And then you put in a filter with the particular light wavelength that is emitted by oxygen. You know exactly where these are because you can do lab experiments that tell you oxygen emits at this wavelength, sulfur emits at that wavelength. So you can define your filters accordingly. And that's what they did when we look at the color here. They decided that this particular object seems to contain quite a lot of hydrogen, oxygen, and sulfur. Notice that sulfur and hydrogen actually have very similar colors in the sense they both emit in the red part of the spectrum, but at different wavelengths. And so a narrow filter that picks out the sulfur will show you where the sulfur is. A narrow filter that picks out the hydrogen, even though it's fairly close, you can make these filters fairly narrow to make sure you're only picking out the hydrogen. And when it comes to how are we going to represent this image, well, there's no point in having the sulfur and the hydrogen both red, because how are you going to tell which bits of your nebula are sulfur and which bits of your nebula are hydrogen if they're both colored red? So they simply arbitrarily decide, well, I'm going to color the sulfur image red, I'm going to color the hydrogen image green, and I'm going to color the oxygen image blue. It's somewhat arbitrary, except that where possible, they always try and keep the same order. In other words, it's always longer wavelength on the left and shorter wavelength on the right. And when it comes to the red, green, blue, the choice of which way round are you going to do this, they always try and make sure they keep them in the same order. So hydrogen can't be red because we're already using red for sulfur. So hydrogen gets placed in the green slot and oxygen in blue. And then we generate these three images from these three wavelengths and add them all together and get the final result. So no, that is not what you would see if you were standing in front of the Pillars of Creation. It would not be a blue background because that blue is coming mainly from oxygen. There's a certain amount of blue in there, but it's dominated by hydrogen, which tends to produce this green color in the background. You would not see a strong green. If you were standing in front of the pillars of creation, you would be dominated by the sulfur and the hydrogen. So the pillars of creation, for anybody that's actually photographed the Eagle Nebula with a standard RGB filter, it comes out quite definitely red because you can't see that much oxygen. It's exaggerated in this particular way of combining the images. So the pillars of creation are actually red because of sulfur and hydrogen, but if you separate them like this, you get artificial colors, the so-called Hubble palette, that allows you by eye to start to say which bits are hydrogen, which bits are oxygen, which bits are sulfur, because you've separated them out into three somewhat arbitrary colors. As I say, there's a tendency to try and keep them in the same order to make sure that there is some sanity to how you represent different wavelengths as different colors in your final color image. And remember, the wavelengths that we can see are only a tiny part of the electromagnetic spectrum, and in principle, you can apply the same idea as the Hubble palette, regardless of which particular wavelengths you've picked out. The fact that sulfur, hydrogen, and oxygen were picked out of the visible spectrum is neither here nor there. You can pick any three wavelengths you like. They could be in the ultraviolet or the infrared, and you can still say, I'm going to choose this wavelength and make it red, this wavelength and make it green, this wavelength and make it blue, and make myself a color image. And that's precisely what the James Webb has been doing for the last 5 years or so. It has a very complex filter wheel. In fact, it has multiple filter wheels, and these various filters in the filter wheel can be dialed up to let through only the light of hydrogen, or only the light of sulfur, or only the light of oxygen, or not quite any element in the periodic table, but they've chosen dozens of different elements that they think will be present in various objects, in various nebulae, in various star-forming regions, etc. And they can dial up any of these and then combine them together in any particular mix they like to give them what is hopefully a scientifically useful, meaningful image. This on the bottom left is just an indication of some of the filters they have available. You can't see the scale, but these are various infrared wavelengths, and some of them are relatively narrow to pick out only a very narrow range of wavelengths. Others are more broad or very wideband, depending on the particular object that they are trying to image. So the takeaway messages from this talk is: the eye is not a camera. It is very, very different from a camera. The eye has got an awful lot of processing of color information as well as spatial information before those signals are fed to the brain. So what you think you see is often not what is actually there. Hopefully a camera gives you a faithful rendition of what is the amount of light in the red and green and blue part of the spectrum, much more reliable than the rather subjective indication we get from what we think is actually there. The colors of stars are determined by quantum theory, so-called black body radiation, and it depends on the temperature of the star, and it varies for red stars at the red end of the spectrum. As the stars heat up from red giants through to something like the sun, it's mainly white, and if we go high enough, the peak of the radiation is in the ultraviolet, and then we get a tinge of blue coming into the spectrum. But you will not find any images that have emerald green stars. There's just the slightest hint of color when you've got all the colors represented, but definitely cool stars are red, hot stars are bluey white. And when it comes to nebulae, that's determined not by the temperature of the object, it's determined by which atom is emitting or absorbing the light. We have discrete or line emission spectra or line absorption spectra, and it depends entirely on the constituent atoms. So that's really handy, because if we can measure what those wavelengths are, we can effectively find out what these things are made of simply by looking at the colors that they are emitting. And breaking down light, the colors of light, into a spectrum and analyzing and quantifying all of those colors allows us to look at spectral lines to see if stars are moving, very useful for working out whether we've got exoplanets, for instance. We can also determine what things are made of, because as I just mentioned, we can work out atomic composition by looking at where these particular emission lines are. And as I indicated, we can also use them for determining redshift. either spectroscopically or even just by looking at light at different colors in very crude chunks of the spectrum, not necessarily a detailed spectrum, but we can use that to determine recession velocities and hence distances at vast distances into the universe. Thank you very much.